So hello everybody, I'm talking to you from the UK. So it's getting pretty late in the evening for me. But I'll be presenting some work I'll be doing with Ariel Deutsch on looking at the origin of water ice in simple lunar protocraters. The presence of water ice at the lunar poles is now well established, and these normally come in two different varieties. The majority of them are likely to be cold trapped. These are within impact craters, normally simple impact craters, or possibly seen at exposures on the surface of the moon. But what we want to answer here is what is the origin and potential age of this ice? So the ice could be young or the ice could be old. The ice could be young if it was in place after the formation of its host body. So in this case, it would be likely longer than about 3.5 billion years, so in place after the formations of the impact craters that it's found within or on top of. Alternatively, the ice could be old. In this sense, the ice was already buried beneath the lunar surface and was then excavated or exposed by the crater forming impacts up to about 3.8, 3.7 billion years ago. So in this particular research, we were looking at the latter option, investigating whether the ice is old. So determining how these impacts can redistribute ice buried beneath the surface. And specifically looking at the conditions under which these layers can be excavated and preserved to the lunar surface. And so some of the implications for this are to look at what the stratigraphies of the ice-bearing craters are, and also infer the ages and sources of these ice. This can also be useful for missions to look at the lunar South Pole, so for example, the Viper mission. And as we take a numerical modeling approach to this, it should also give us insight into the influence of ice layers in the formation of simple craters. And this would build upon a work that focused on Shackleton crater by Hallam et al., which was published last year. So onto our methods. To numerically model these simple cratering events, we use the iCell shock physics code, which has been used extensively to model impacts on the moon and other bodies. On the moon, it's been used for everything, as I said, from Shackleton crater, a small simple kind, all the way up to South Pole Aitken. We used a typical impact velocity range of 10 to 20 kilometers a second, which is suitable for the time of the crater bombardment on the moon. And as we were interested in forming simple craters up to about 15 to 20 kilometers in diameter, we limited the size of our impactors to diameters of between 0.5 and 2 kilometers. The setup of our moon consisted of two layers, a crustal layer, which was represented by an equation of state for gabbroic anorthosite. This again has been used extensively as a crustal analogy for the lunar crust. We used dunite to represent the impactor. And then for our ice layer, we used a wet tuff equation of state. This follows the same approach as the Hallam et al. Paper. And this was partly done due to the fact that we weren't necessarily interested in looking at a solid ice layer. The ice would likely to be a mix of ice and rock and other materials. So that's why the wet tuff equation of state was chosen to represent this particular ice layer. This ice layer was placed at various thicknesses and depths within the crust. So it had a thickness of up to 1 kilometer, representing gigaton deposits of ice. And the depth of the ice was varied up to being 1 kilometer beneath the surface. Okay, I will move on to results and show you two simulation videos of two varying scenarios to give you an overview of what we see. So this first video will show the impact of a 1 kilometer body impacting at 10 kilometers a second, where the ice layer is 1 kilometer thick and 1 kilometer, originally 1 kilometer beneath the lunar surface. On the left, you see the material setup as you've seen previously in the previous slides, and on the right is showing the peak shock pressure of the material. So once I start the video, you will see the initial opening up of the transient cavity. You will see this collapse. So keep an eye on the dirty grey layer, which represents the ice. So we can see in this impact that the ice itself isn't excavated. The excavation depth is within the top layer of crust. We see crusted material tends to pool at the bottom of the crater and is fairly highly shocked, as you would expect. What we do see, though, is the exposure of ice material on the crater wall and the formation of an ice platform as well, which has some highly shocked crusted material on the top of it. So in this particular scenario, we don't see ice being excavated during the transient crater stage, but ice is exposed during the modification and the collapse stage. Sorry. This is the a comparison video. Here, the conditions are the same, but the impactor is just 0.5 kilometers in diameter. So I will play the video. And as this is a less energetic impact, we see that the transient cavity again doesn't reach the ice layer. We also see that no ice is exposed at the surface. Thank you. We see that crusted material again is pooling in the center of the crater, and we generally have a standard bowl-shaped crater forming. So this scenario saw no ice excavated or exposed. So that's just two examples. What we tend to see over the range of impacts that we looked at was that the ice layer was excavated or exposed in limited scenarios. It was mainly found on the crater walls. And the ice generally seems to be shocked to low pressure, but further work is needed to see what the latent temperatures or pressures for melting and vaporization would be. And then this is my final slide. So what we saw was that the water saturated material could be exposed at the lunar surface and not significantly shocked. But the final location of this material is heavily dependent on the impact and the target parameters. So it's likely to be a small parameter range where this outcome is likely. The formation of the platform could tell you something about the influence of the ice layer on the formation of the crater, but more work may be needed there to see whether the equation of state is as suitable as it could be. So that overall, this is saying that we seem to think that some lunar ice deposits may be old, they were in place before the craters formed, and this would be consistent with Monte Carlo ice deposition modeling and regolith garden processes, which would suggest that ice was delivered in episodic episodes very early on in lunar history. Thank you very much.
All right, I think we have time for one question. Oh, we have someone heading over.
Okay, Margaret Landis, see you last. My question would be that if the emplacement is episodic, but over multiple episodes, do you take into account any sort of regolith layering within that ice or plans to do that in the future? And how might that affect your results?
That's not something we've considered here. Given the nature of the modeling, the layers are sort of consistent thicknesses with only one layer for now. So it is something that we could look into in the future. But yeah, we're just looking at sort of simplified versions for now, just to see what scenarios could be to expose or excavate this ice material.